Now, we've learned about the orbitals, we've learned about the shells, we've learned about how many electrons can be in each of the orbitals in the subshells SPDF. SPDF are just subshells found in the shells, which is n equals to 1, n equals to 2, n equals to 3. We know that by now we know that the s orbital carries a maximum of 2. Each of the p orbital carry 2, but there are 3 of them, so 6 for p, 10 maximum for d because he has 5 orbitals in the d subshell. Then you have 7 orbitals in the f, so 14 electrons. Each orbital is 2 electrons. Okay, so since we know this, now we can do what we call electronic configuration. What is to configure? To configure is to set up or to arrange. So let's describe electronic configuration, which is electron arrangements in these orbitals when looking at atoms of elements. So the electronic configuration shows how electrons are arranged in the atoms orbitals, and we know what orbitals are. It's just the spaces where electrons reside or live. The ground state is the lowest energy arrangement, like the best arrangement possible that it's likely to be found in nature in the structure of an atom. There are rules followed to determine the best, in other words, ground state electronic configuration of an atom. Rule number 1, electrons are placed in the lowest energy orbital, beginning with the 1s, beginning with the first shell and then the 1s orbital. Orbitals are filled in order of increasing energy. Pause. We go back to the structure of the atom. Okay, so we are saying you have to consider n equals to 1 first. Fill it up before we go to n equals to 2. Now, in n equals to 2, you'll have to fill up the 2s before you fill up the 2p. And then you go to n equals to 3. In n equals to 3, you have to fill up the 3s before you fill up the 3p. And it's going to be the first time you see the d before you fill up the 3d. And then if you go to the fourth shell, n equals to 4, you'll have to fill up 4s before you fill up 4p, before you fill up 4d, and it's the first time you're going to see the f in that order. So you're feeling going this way. N equals to 1 is going to be the least energy principal quantum energy level or shell. And in there, you just want to fill up the s. It's only the 1s that's in there, which is what is being stated here. That is rule number 1. I hope you understand now. The rule number 1 can be also illustrated here. You see how I showed the circle here? The rule number 1 can also be illustrated using this energy level orbital diagram. Now let me break this down to you. Assume that the nucleus is right here. So the first energy level, n equals to 1, will be there. Okay. And then I change my color. The second energy level is going to be somewhat here. He's going to contain the 2s and the 2p. Remember, the first energy level is just the 1s. Okay. So here we are just including the 2s and 2p. Okay. That's the p orbital cut into 3 boxes. S is just 1 box. Now the third shell is gonna be somewhere. The third shell is gonna be somewhere arranged somewhere here. So this is n equals to 3. Now because the energy between the 4s and the 3d is quite close, and usually the s is the closest to the nucleus, when filling up, we fill up the 4s before the 3d. But generally, n equals to 3 contains 3s. Okay, you see there. It contains 3p. You see there. And it contains 3d. You see there. But some electrons, usually electrons will jump from the 3 to the 4s before they fill up the 3d. We'll talk about how to fill up these shells using something that looks like a Pascal's triangle. But for now, just know the rule is that we always fill up the 4s before 3d, because the 4s has an s orbital which is happy to be close to the nucleus, and the energy between these two is usually very close. So we usually just fill up the 4s before we fill up the 3d, then we go to the 4p. Okay, so the fourth shell is roughly somewhere there. So again, if you're at n equals to 4, you have the 4s, you have the 4p, sorry, and then you have the 4d, and then the first time we see the f will be in here. However, the rule also applies here. You want to fill up the 5s before you fill up the 4d, and then you can now skip and now fill up the 5p. Then you will have to fill up the 6s before you fill up the 4f, because we have to account for the 4f. So there are irregularities in filling up those orbitals once you hit the 3p level. But you get the idea. The lowest energy is going to be the first energy shell. Now that was rule 1. Let's talk about rule 2 of electronic configuration. Rule 2 is that each orbital holds a maximum of 2 electrons. Oh, you know that. I told you that anytime you're having an s, or one s is gonna just take the 2 electrons. Now if you're looking at the p subshell, he has 3 p orbitals. Like you have px, py, pz, 3 types of p orbitals, but they are all same energy. But again, each orbital carries a maximum of 2 electrons. Same with the 3d, it has 5 boxes. Those boxes are orbitals. Each of those orbitals will carry a maximum of 2 electrons. Then comes rule 3. When orbitals are equal in energy, 1 electron is added to each orbital until all of the orbital is half filled. So example, let me give you an example here of this rule. Remember how I talked about the p subshell and said that it's divided into 3p orbitals, px, py, pz. Suppose all you have is 3 electrons. You want to singly occupy them using 1 electron at a time. This is the wrong thing to do. The wrong thing to do is to do this, leaving this empty. That is a felony in chemistry. Someone needs to be jailed for a long time without bail and parole and food. Okay, so this is the correct way to do it. All smiles. The next part, then the orbitals can be completely filled. Now suppose this is when you had 3 electrons left. Suppose you have 4 electrons left after populating the earlier orbitals. You'll do the same thing, populate them singly before you start pairing to fill up the rest. So that is rule number 3. Okay. Now, an orbital diagram, which is such that you see in this slide, an orbital diagram shows you the energies of each orbitals as you go. By the way, whenever you have such equal energy orbitals like the ones in p, the word used is these orbitals are degenerate. So if you ever see that in the quiz, in the homework, it just means that the orbitals have the same energy. They are all p's, they have the same energy. Now let's talk about orbital diagrams. I digressed a little bit. An orbital diagram uses a box to represent each orbital and arrows to represent electrons, something you've seen me doing a lot. Now, I don't like us showing full arrow like that. Usually it's half arrows. Okay, so this is an orbital. It could be an s, a p, a d, a px, a py, a pz, but those ones are usually populated. Those are representations of orbitals populated with electrons, like that. So the 2 electrons must have paired spins of opposite directions. This again is another felony. You don't want to do that because electrons have equal charges. So what we do, like charges repel. So what we do, we invert one. It's just like when you have a magnet with the north pole and south pole. You don't want to bring the other one north. No, the magnets will repel. So it has to be south and north so that they can pair up. Electrons are baby magnets, are tiny microscopic magnets. Okay, so you want them to have opposite spins, opposite directions. In physics we'll call them spins. Okay, now let's try and do some electronic configuration. So remember, this part is majorly covering electronic arrangements, or use the fancy word, electronic configurations or arrangements. So if you look at the hydrogen in the periodic table has one proton. It has one proton. So by inference, we can say it has one electron because the atom has to be neutral. One positive and one negative will cancel out. So we're going to use the atomic number Z equals to 1 to predict the number of electrons. So that's how this is predicted, because Z is just the number of protons, atomic number. So if you're looking at the Bohr atom, the hydrogen atom, he is going to only have one shell, n equals to 1, and we know that that's where you're going to see the first s. Now we say that the s orbital carries a maximum of 2 electrons, whether it's 1s, 2s, 3s, 3, 4s, or whatever. Now since we only have one electron to account for, that's the only one we're going to put it in the 1s. That's the orbital notation for it. So the electronic configuration will in turn be written as 1s1, where the 1 is the shell number or principal quantum energy level number. So that's the shell number, and then the s is the type of orbital and could also represent the subshell. And superscript 1, that's just the number of electrons we are counting for. Remember, we knew we had one electron because we knew the atomic number of hydrogen is 1 with one proton. Okay, so electronic configuration of hydrogen will be 1s1, with this preceding one is the shell number, and this superscript 1 the number of electrons in hydrogen atom. Now if you look at the case of helium, which is the next smaller element, the helium has 2 protons. So helium has 2 protons, so the atomic number Z is 2. That means you have 2 positives, so you need 2 negatives, and that comes from the 2 electrons. So anytime you know the atomic number, it will be the same value for number of electrons, which we need for electronic configuration. Okay, so helium has 2 electrons. Now how do we arrange the helium electrons? So we have the nucleus, and then we have the first shell. The first shell, n equals to 1, has s orbital, and each orbital we know carries 2 electrons. So that's how we would show the orbital notation, with the electrons have fishhook arrows up and down. That is the electrons in the 1s. Now for the electronic configuration part, we'll write it as 1s2, where the 2 here is the number of electrons in this orbital. Okay, so we are showing how to arrange electrons. Now we go to lithium. Lithium has atomic number 3. Now you know the drill. If you have 3 protons, therefore you have 3 electrons, and you're probably going to fill up the 1s first with 2. You're remaining with 1 out of the 3. The third one is going to go to the 2s. Okay, and then the electronic configuration can be generated from the orbital notation. So the 1s had 2 electrons, the 2s has 1 electron, That totals 3 electrons that we started off with. Now, carbon has 6 protons. If you have 6 protons, that means 6 positives. We need 6 negatives. That comes from the 6 electrons to match that, because the atom has to be neutral. We talked about that. And if I am to spread these, the 1s is going to get 2 electrons. Then we go to the 2s following the energies. Remember, we fill up coming out of the nucleus from the first shell, second shell, third shell, where n equals to 3 and so on. So 2s will get 2 electrons, and then 2p. Remember, the p always has 3 orbitals. The p subshell has 3 orbitals. Px, py, pz. So assume this is px, py, pz. Since the 1s and the 2s have taken 4 electrons already, what we need to do is to take the extra 2 electrons in the p, and remember the rule that told us that you don't pair up first. You singly populate before pairing. This is going to be legally left empty. There's no more electrons to put there. So if you look closely, the 1s has 2 electrons, so 1s2. The 2s has 2 electrons, 2s2. And the 2p has total of 2 electrons, 2p2. And that gives you the electronic configuration of carbon. Neon has 10 protons. So 10 positives. He needs 10 negatives, and those who will come from the 10 electrons. Now again, the first shell n equals to 1 will carry 1s. The second shell n equals to 2 will carry 2s, and the first time we see the 2p. Now if you list them here, s carries a maximum of 2 electrons, so 1s2, you see it there, 2s2, you see the 2 in the orbital notation, and then out of the 10 we've accounted for 4, we are left with 6. Those 6 will have to follow the rules. We have to do these, so singly populate, and then now we pair them up. That's how those 6 will go into the p, and that gives you this electronic configuration of neon: 1s2, 2s2, 2p6. Okay, so before we talk about the noble gas notation, let's do some practice of electronic configuration. I'm going to give you a shortcut on how to follow, how to know which orbital is filled first. Let us look at a bigger element like let's look at bromine. See, bromine has 35 as the atomic number, meaning it has 35 protons. Let's work on that and find the electronic configuration of bromine, shall we? Okay, so bromine has atomic number 35, as we have seen in the periodic table. This tells me that he has 35 protons. This tells me that those are 35 positives. We need 35 negatives to neutralize them. So I know that the number of electrons is going to be 35 for this bromine. Now what I've put here is kind of the process, a guide to show you who is filled before who. And I'm showing you here the shells, or what you call the principal quantum numbers. As you fill them up from the lowest energy, which is the shell closest to the nucleus right here, you have to fill up the first circle before you go to the second circle, third circle, and so on. So I'm showing you the trend. Usually I use this as a guide. This is the to go to. Now before I continue, I'll have you take a picture with your cell phone. Just take a picture of this thing. It will greatly help you in test 1 coming very soon. So what I've drawn here, I've written, or it's written 1, 2, 3, 4, 5, 6, 7, 8. We started at 1, and all those are S's. Those are S's. And then I go to the P. The P, the first time you see the P is in the second shell. You see the P is seen in the second shell. So start from number 2 this time around. Don't start at 1. Start from number 2. 2p going down whichever way, however far you go down. For me, I usually just stop at 7. And then after the P, we go to the D. The first time you see the D is going to be in n equals to 3. So start at 3. 3D, 4D, go on, and then the next column will be the F. The first time you see the F will be in the fourth shell. So 4F going on. Now, after you do that in your worksheet or in your paper, I know you've taken a picture as I instructed you, just follow the arrows. You fill the 1S before you fill the 2S, before you fill the 2P, then the 3S, before you fill the 3P. Notice that after 3P, we don't go to 3D, we go to 4S. Put a star there. Then after the 4S, you fill up the 3D, and the reason is the 4S tends to have a lower energy than the 3D. So what do? You just follow it the way it is. It's nature. It is what it is. So fill up the 3D before 4P. Then you fill up the 5S. Now you're filling the 5S before the 4D. Why? Again, the 5S, put a star there. 5S has lower energy than 4D. Okay, so fill 5S before 4D. Then you come back and fill up the 4P. We can put a star there. Then the 6S before the 4F, because 6S has lower energy than 4F, and the trend continues, so and so on. So you see, this is an important guide. Let's get back to bromine. We have 35 electrons to account for. So I'm going to have 1s2 filled up. S carries a maximum of 2. Now I'm on 2s, so I go to 2s. I'm following the arrow, the tail of the arrow. I go to 2s, S orbital carries a maximum of 2. Those are 4 electrons out of the 35. Next, after 2s, where do I go to? I'm going this way. I'm at the 2p. So 2p, p has px, py, pz. He carries a maximum of 6. Now those are 10 electrons accounted for. After that, I go to the 3s. 3s carries a maximum of 2, the s orbital. Then after 3s, I'm following my arrow. I'm going to 3p. 3p carries a maximum of 6. So far, I have 18 electrons accounted for. We still keep going. Then I'm going to go to 4s first. So 4s carries a maximum of 2. After the 4s, I'm trailing. That's the time I'll get to 3d. 3d carries 10. How many electrons have we accounted for so far to that point? So I have 10, 10. These are 30 electrons. So there's 10. 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is 10. Plus 10 is 30. So I'm left with 5 out of the 35. So from the 3D, I go now to the 4P. So 4P is right here, and he's going to carry the remaining 5. Okay, now what was the outermost shell? That is the complete electronic configuration. Let me name it. This is the complete electronic configuration of bromine, what we just wrote. What is the outermost shell? The outermost shell is the fourth shell. You see it? So if I come down here, I have 4s2 and 4p5. This is the outermost shell, and the outermost electrons are 7. And that is why we find Br in main group 7a. Okay? Because the outermost electrons, what we call the valence electrons, outermost electrons are valence electrons. Turns out they are 7 valent electrons. So bromine is found in main group 7a, and that 7a, we called it the halogens group. Does that make sense to you? Very good. If you go to the periodic table, you'll see bromine is right here. It's in main group 7. Better yet, I can show it to you in your notes when we talked about main group 7. Let's go back up. So electronic configurations helps us to put electrons where they belong. See, bromine is right here. That's where bromine is. He is in main group 7 because the outermost electrons in the fourth shells counts to 7. Now, that is a complete electronic configuration, but I want to show you something else that's coming up in the slide. That's a complete electronic configuration. Call this A. Part B, you might be asked to write the noble gas electronic configuration of bromine. How do you do that? The way you do that, you look at the complete electronic configuration. Let us write it here. And then identify the orbitals that are fully filled, the shells that are fully filled, so to speak. Okay? So I can tell that for sure the first shell is filled up, the second shell is filled up, and the third shell is filled up. Okay? I can tell that for sure. Okay? But you realize that the third shell is marked between the fours, right? So let's just focus on these ones right here that are filled up. How many electrons are those? 2 plus 2 plus 6 plus 2 plus 6. Those are 18 core electrons. Which noble gas, since we are trying to shorthand the long complete electronic configuration to a shorter way to write it, we look at the most filled orbitals, and then we look at the noble gas that has the same number of electrons in the periodic table. Which noble gas has the same number of electrons in the periodic table? It's gonna be argon. See, argon has 18 protons, meaning 18 electrons. So all these core electrons or core orbitals and core electrons can be summarized as argon in brackets, and then anything that is not core is going to be written on the outside. Okay, now I want you to do one more thing. Look at the outside shells. How many electrons do you have in there? If I sum up 2 plus 10 plus 5, I get 17 electrons, which is why, again, you'll find that bromine is found in overall group 17b. Let's look at your periodic table. You see how it's written 17 right there? Here, it's 17, and that's where the bromine is found. So again, including the 3D, you can tell that bromine is found in overall group 17 and main group 7. Main group 7 is decided based on the number of electrons in the outermost shell, 4s and 4p. So I've shown you two things: how to write the electronic configuration, the complete electronic configuration, and the noble gas. Let me do one more here. I'm going to use a simpler element. This time let's use sodium. What is the atomic number of sodium? Going to the periodic table, sodium is right here. It tells me it's 11 protons in there. So he has 11 protons. So 11 protons means 11 positives. We need 11 electrons to give us 11 negatives to cancel out the 11 positives. Okay? So that tells me that if atomic number is 11, that tells me that the number of electrons still gonna match it is gonna be 11. So the electronic configuration, we follow the trend. It will be 1s2, 2s2, 2p6. I've accounted for 10 electrons. Then I go to the 3s. So I'm here. I'm just following the trail. It will be 3s1. If you sum up all these, 2 plus 2 plus 6 plus 1, you're going to get 11 electrons accounted for. Okay? So now this is what we call the complete electronic configuration. Pause the video and do part B. Write for me the noble gas electronic configuration of sodium. Pause it there. Do it. Okay, so now this is the answer that you should get. Firstly, write the complete electronic configuration, and then identify all the filled up shells, which will be these guys. We call those core orbitals, and the electrons in them are called core electrons. This is going to be the valence valent electron, and the third shell is going to be called the valent shell. Now, how many valence electrons we have in sodium? The sodium is seen to have one valence or remaining. Valence just means remaining or outermost. One valence electron, and that is the reason why you'll see sodium in main group 1A based off that. Now, if I'm to write this in the noble gas electronic configuration, I see the green part has 10 electrons, so I'll put that in parentheses, but instead of writing the 10 electrons in there, I'll look for the noble gas that has 10 electrons. It's gonna be neon. Go back to your notes, you'll see that neon in main group 8, let's find it. Neon in main group 8 has 10 electrons right there. So that is going to account for the green part, the core orbitals and core electrons, and then the remaining will be out there. So again, this one valence electrons in the 3s tells me that sodium is in main group 1A, and then these three will tell me something, that it will tell me that the sodium is gonna be in the third row of the periodic table. Let's confirm. You see how the outermost shell is 3? Let's confirm where the sodium is in the periodic table. So sodium is here. You see him just on the third row. So the outermost shell will tell you where the period or the row where the element is, and the valency will tell you the column. The valence electrons will tell you the column. Let's go back to bromine. Remember how bromine had overall 17 valence electrons, so it's overall group 17. Or if you look at 4s2, go back to bromine. If you look at 4s2 4p5, you have 7 valence electrons, so it's found in 7A main group. Overall, it's found in 17, column 17. Now, what is the outermost shell in bromine? The outermost shell is a 4th shell. So that means that bromine is in the 4th row of the periodic table. Let's confirm that. Bromine is right here, and he's really in the 4th row. You see him in the 4th row. Same in your periodic table, summarized periodic table. In your notes, you'll see that the bromine is going to be found in the 4th row. See it? You see it? It's in the 4th row. So the outermost shell tells you the period where it's found, and the valence electrons tells you the column, main group column or overall column where the element is found. I hope that makes sense to you now. If I come back here to the notes, that is the next thing being done here. If you're looking at the second row elements, that is period 2, the electronic configuration can be shortened by using noble gas electronic notation, starting from there going down. Carbon has atomic number of 6, so 6 protons, so you expect it will have 6 electrons. So since he has 6 electrons, following the trend, this will be the electronic configuration. The fully filled shell is only the first one. This P needs more because P would go to P6. So the noble gas with 2 electrons in your periodic table is going to be the helium. Helium, you see, he has 2 protons, 2 electrons. So you shorten that one as 2, represented with the helium in brackets. These electrons on the outside are called valence electrons, and they are living in valence shells. Now look at how many valence electrons you have. How many valence electrons you have? 2 plus 2 is not 22. Come on, it's 4 electrons. So I expect carbon to be in main group 4A. Now since the outermost shell is 2, I expect carbon to be in the second row of the periodic table. Let's confirm that. Remember, it should be in 4A column, and it should be in the second row because you have the outermost shell as 2. So we go to the periodic table, find carbon. He's right here. Carbon is right here. I see him in the second. I see carbon in the second row as lithium, beryllium, and boron. Carbon is right there. He's in the second row as nitrogen, oxygen, fluorine, and neon. He's right here. Now he's going to be in main group 4 because if you count the long tall columns, that is 1, 2, 3, 4. Carbon is found in main group 4 because of the 4 valence electrons. Okay. All right. So the noble gas electronic configuration of carbon would be helium 2s2 2p2, but the complete electronic configuration is 1s2 2s2 and 2p2. Now let me give you a shortcut on how to decide which noble gas will give you the shorthand. Okay, so if you're looking at your periodic table here in the notes, you'll see that the carbon is right here, right? That's the carbon. Let me change to red. This is the carbon right here. If you go above, you'll see the helium. Now this is the bromine right here. If you go above, you see the argon. That is why I used argon. I used argon here in the noble gas electronic configuration of bromine. What about sodium? If you look at sodium, sodium is right here. Right above the sodium, go to the noble gases. I'm going to draw in purple. Right above the sodium, you see neon. Above, you see the neon. So we use neon to write the electronic configuration of sodium, which is what I did down here. I used neon for that reason because sodium is here and neon is right above it. That is how quick you can decide which noble gas to use in writing electronic configuration of these elements, especially the shorthand, the noble gas electronic configuration of these elements. Now let's look at calcium. Calcium has atomic number Z equals to 20, meaning it has 20 protons, meaning it has 20 positives. So to get the 20 negatives, you need 20 electrons right there. Okay, and the electronic configuration, this is an orbital notation, filling it up: 1s before 2s, 2s before 2p, 2p before 3s, 3s before 3p, 3p not to 3d, you fill up the 4s first. I explained that. So s will get 2, 2, p maximum is 6 because he has px, py, pz. S is 2, p maximum is 6 because again you have px, py, pz in the 3p, and then 4s maximum is 2. That is the electronic configuration which is written here. Now if you want to find the noble gas electronic configuration, go to your periodic table. Which noble gas is found above calcium in the periodic table? Calcium is right here. Let me choose black. Is that black? Let me choose black. Calcium is right here. The element above him in the noble gas is argon. So we're going to use argon for our shorthand. Let's go back to our slide. Yep, so we choose argon. Now if you choose argon, those are 18 electrons represented by him because argon has atomic number of 18. So these are the core orbitals that you're going to go for. Those are the ones you're going to go for because you need 18 electrons. I know you have 3D somewhere, but it's not in the picture here right now. So these are 18 electrons, and those are short-handed by the argon. 4s is the valence shell number 4 with 2 valence electrons. Now, I'll tell you again, since you have 2 valence electrons, outermost electrons, okay, I expect calcium to be in main group 2A. And again, I have 4 as the outermost shell, so I expect calcium to be in the 4th row and second column. Second column based on valency, 4th row based on the valence shell. To confirm that, let's confirm that calcium is in the second row, second group, second column, and 4th row. Again, I'll take you to your periodic table in the notes. You'll see calcium is an alkali earth metal, and he is right there in main group 2 and is found in the 4th period. So electronic configuration is quite important. It helps us to position these elements in the periodic table. So I believe to that point you already have a picture, so the rest of the examples will be easy for you. Now, since the calcium has an S at the end, we say that calcium is an S group element. Calcium was somewhere here. It's an S group element, and he ends up with a 4S. You see that? What about bromine? Bromine ended up with, we had 4S, I believe, then 3D, then 4P. So bromine is somewhere right here. It's a 4P, or it's a P block element, while calcium was an S block element. If you do the electronic configuration of transition metal elements, you'll always end up with D orbital. So transition metal elements are D block elements. Okay. Now, if you take chlorine, for example, with atomic number 17, you go 1s2, 2s2, 2p6, 3s2, and then 3p5. So chlorine is right here. You see it's gonna be having a 3p, is a 3p element, it's a p block. So chlorine is a p block element. And the valency, 2 plus 5 gives you 7 electrons. Valency of 7, chlorine is found in main group 7. You'll see it right there. If you are to write this in noble gas notation, this is what will help you, because right above chlorine is neon with 10 electrons. So I'll use neon to shorthand, and then it will be 3s2, 3p5. Outermost shell is 3. I see chlorine in the 3rd period. I mean, electronic configuration just tells you everything. Now, these lanthanides and actinides, those are called the F block elements, and which is why they were sliced out of this part because of that reason. They end up with an S. They end up with an F, not a D. So they were sliced out and put down here by themselves, because the electronic configuration will always end up with F.